Now let me start the recording. So the topic today is automated machine learning. This is by far the most important topic in recent times. If there is one thing that will completely change the landscape, I think in the coming years of how we do machine learning, um, it would be this topic. So I'll talk a little bit about that. I won't cover the all of automated machine learning, though I would cover two of its biggest pieces. Now, along with that, I'll also cover a research paper which is on COVID. Now, actually, I'd like to start with that research paper and sharing that so that we see something about it. All right, let me share my screen. So by the way, guys, are you okay for extending this thing up to 10 p.m.? Or does anybody have a hard cutoff?
Yeah, that's fine.
That's fine, right? Okay, so that gives us some breathing space. So guys, this is Nature. Nature, as you know, is perhaps the most prestigious scientific journal, or you get your articles in Nature if people believe that you have a true breakthrough. So this is one of them. We live in COVID times. Any and all effort these days is devoted to COVID. All kinds of researchers are trying to contribute. So one of the things people asked is, can AI look at people's chest X-ray and detect uh, COVID? Right? Now, that's a provocative question. If you remember, one of your second project, which you may or may not have the time for, is to look at chest X-rays and detect lung cancer. And nowadays, there has been a tremendous amount of success. People have been able to look at the structure, the MRI and the X-ray of the human heart. And in some cases, the AI is able to spot anomalies in the heart that were so subtle in the heart muscles, cardiac muscles, and the circulatory system that were so subtle that it missed even the most experienced cardiologist. And so these are all little bits, remarkable insights. However, the fact has remained that the medical community, to a large extent, has remained sort of on the fence. They're skeptical whether it works or not. So we are in a transition time. AI has made a lot of progress, but still it's in some areas it has made fundamental breakthroughs, like for example, in the protein folding. Uh, News that I talked about last time, which is truly a remarkable breakthrough for AI to do. And again, a tremendous and unexpected achievement for transformers, attentions, and so forth. But there are also areas in which AI has been trying for a long time and has not been able to make a dent. Part of the reason it has not been able to make a dent is when you try to create deep neural networks, quite often you don't know how the network should look. There are too many variables. Should I make it should I make it out of 10 layers, 20 layers, 100 layers, 50 layers? How many layers do I need to put? What should I put there? How many layers of conv? How many filters? How many max pooling? What are the residual short circuit connections? You see that we get into this world in which there's a combinatorial explosion of possibilities. How many nodes per layer and so on and so forth. None of it is clear when you hit data. So we tend to take an existing architecture, apply it to that data, and from there start evolving, hacking from there. We do this, we do that, and we see if that works. So a lot of deep learning after you picked up the theory and you start working on some real world problem, it becomes hacking day after day, experimenting and seeing which experiments work, which hyperparameter combinations or which neural architecture is giving you good results. So it's a lot of trial and error. So the question has been, that is there a systematic way we can go about it, right? Because these trial and errors are extremely expensive. So think about it. So to simplify it, actually, I'll step out of neural networks. So think of a basic thing. Let's say you think of a random forest and you want to use random forest to classify uh, potentially whether somebody has COVID or not. Now, let us say that random forest had reasonable accuracy and you're just trying to improve it. There are too many hyperparameters, the number of trees to grow, the depth of the trees, isn't it? Then so on and so forth, right? And so uh, with all those hyperparameters, even which one to use, Gini and this and that, entropy, there are many hyperparameters. So for each, and then of course the learning rate. Now, which of these hyperparameters and the regularization parameters and so forth. So what in any algorithm you have that. Now, what happens is that, well, in trees, of course, the number of trees is the regularization, forest is the regularizing. Now, with all of these, it's hard to know what values to take. Right? Another example is the support vector machines. Support vector machines are extremely effective, but you need to specify, for example, which kernel would you use? Would you use a linear kernel? Or would you use a polynomial kernel? Would you use a tanh kernel? Would you use a Gaussian RBF kernel? Let us say that you decided on a particular kernel, polynomial, which degree? RBF kernel. Well, what is your cost function? What is your gamma? Right? And whichever one you care, of course, the cost function is across all of them. How big is your budget? If you remember the theory of support vector machines, the most crucial thing is what is your budget for mistakes? The C, right? And gamma, of course, intuitively speaks to how far one particular lighthouse is spreading its light. You know, that's the intuition I remember giving you guys. So with all of these, you have a lot of hyperparameter. Training a support vector machine on a reasonable sized data and a few hundred features, or even if a few dozen features, can often take half an hour, 1 hour. Now, suppose you take 10 values of the cost and 10 values of gamma. You're already looking at 100 potential experiments. You're searching through that. And then 100 times half an hour is 50 hours. You're looking at a couple of days for the runtime to tune that machine. Now, this becomes even more problematic when you talk in terms of a deep neural network, or even before we go to deep neural network. See, as I said, there is a no free lunch theorem. You don't know whether support vector machine is the best algorithm for that problem. No free lunch theorem says that you can't tell till you have engaged with the data, you would never know. Right? So the algorithm that you pick, even if you're doing a classification, the algorithm that you pick itself is a hyperparameter. And you have to search the space of algorithms to find which is the best one. And what is the tuning parameters for that? Give different values to the tuning parameters for that. So by the time you have zeroed into this, you realize that the number of combinations there's a combinatorial explosion of how many experiments you'll have to do, how many models you'll have to train before you come to know, or you pick the best of them. Are we together, guys?
Yes.
Right? So that is the crux of the problem. And when you come to neural networks, there is an additional complexity. The neural architecture itself is fluid. How many layers? Do we use conv or not? If you use conv, how many filters in each layer, and so on and so forth. There are many hyperparameters of things. The architecture of the neural network itself is one hyperparameter of sorts, isn't it? So people have asked, how do we solve this problem in a systematic way? And so that will be the topic of today. And we'll do that. But before we do that, I wanted you to see this paper. This is a very nice paper, actually. This paper asks this question that can you detect COVID from X-rays? Now, the problem that this paper comes up with is that we don't have enough data. We can create neural architectures, but we still need data. So this project is divided into two parts. One is the COVID net, the neural network architecture, and the other one is the COVID-X, the data behind COVID. And what they are pleading, and they have been pleading now for many months, is for governments and organizations to contribute data. Data is still very sparse, and deep neural network, as you know, needs a lot of data. Well, even with the data that they have, actually this model is remarkably successful. Um, it hasn't beaten the state of the art, which is, of course, the reverse, what is it? PCR, reverse transcriptase, PCR, is that the right word? Um, right? So, which is obviously a very good test, but not good enough, it seems, because it also has an error rate. But it's better than what AI has achieved so far. Now, one would like to believe that once more data becomes available, this architecture would succeed. If it does succeed, it would be a breakthrough because it means that you can get results for COVID testing literally in a couple of seconds rather than, because that's what it takes to do X-ray, or maybe half a minute, rather than days, which is what it takes today to get an accurate reading. Now, this is reasonably good. It's not bad, but it's not the state of the art. Right? Now, what is interesting about this paper is something that I would like to show you guys. They go up, and I would give this paper as a reading guide to all of you. This came as a preprint a long time ago, and I think I've mentioned this to you in the previous classes or in the intro itself. So what you're looking at is a human, this particular thing is the X-ray of the lungs, and you're trying to determine whether somebody has COVID or not. Right? And if you look at it, the top one is a person who's not infected with lung problem or with COVID. The bottom one is a person who is infected with COVID. Right? So qualitatively, they look different, though it's a little hard to tell very tangibly that which part of the X-ray will you zero in to be a litmus test. There is no very clear path. It's complicated. The COVID is sort of visible in the overall picture, but not necessarily too much in any of the specific parts, I suppose. So these people then say, let's apply a convolutional neural net because it's very good at finding those hidden features that may form a good representation for the disease. And when they do that, they actually get very good results, greater than 80% sensitivity and so on and so forth, like this paper talks about it. Now, I won't go into all that paper. It's a very interesting paper. I won't go into the rest of it. As you can see, it also talks about whether you have pneumonia and so forth. But what I will do is I will look at the COVID net architecture. So I'll just read what is written at the bottom of this thing. COVID net architecture, high architectural diversity and selective long-range connectivity can be observed as it is tailored for COVID-19 case detection from CXR images. The heavy use of a projection design pattern in the COVID net architecture can also be observed, which provides enhanced representational capacity which maintains computational efficiency. Now, it's a lot of words, but what it is saying is that, do you see how many layers there are? There are many, many layers. And these layers have a lot of filters. But what is interesting is, do you notice that there are these residual connections all over the place? The whole bottom, you can see how many residual connections there are. More than that, you also see some longer you notice that there are some cross architectures. From here, you split into two parts, to this one and to this one, right? And there are a lot of crossover kind of a thing. And they feed also into the main pipeline. And then there are some long-term things. For example, output of this goes to this, which feeds many layers later, right? And so this whole business of residual and hybridizing the architecture is such that the first question that it evokes is, how in the world did somebody come up with it? Would that be a fair question to ask? right? Like, for example, you wouldn't, if you were sitting down with PyTorch or with Keras or whatever, you wouldn't think normally or immediately of creating an architecture like this. So how do people discover such interesting and complicated architectures? Would you like to take a guess?
AutoML.
Kate, say that a bit louder, please.
AutoML.
AutoML, yes, indeed. But what does that mean? Like, how would we do that?
Like
Using
throwing
that
some
neural
experiment.
architecture search, like you define range of parameters and then select the best one.
That is more like a hyperparameter optimization, but yes, close. See, guys, what happens is that, think about this. This neural, if you were doing it by hand, you would be putting all sorts of layers together, right? And you would be doing trial and error and seeing what works, isn't it? So why not do a different thing? The whole idea of neural architecture search is that why not create a neural network whose job is, in some sense, this is a very hand-waving argument, whose job is to think through the right architecture, right? Put together the right architecture. And that is what we do. And this paper talks quite a bit about that, how they come upon all of this. Obviously, there's a lot of hand thinking also, along with using AutoML and so forth. But the reason I pointed this out to you is for two reasons. One is that today, the problems that are unsolved are all hard problems, right? And solving them is quite often not so much as just putting, a few lines of PyTorch or a Keras together, but it is thinking deeply. You have to go to the next level, which you don't get to simply by doing what we have learned to do so far. We need to learn something else, right? And that is the future. And that's something else that we'll talk about is this big world, something called a Bayesian optimization. So today I'm going to introduce you to Bayesian optimization, right? And people often say the Bayesian optimization applied to hyperparameters is Bayesian hyperparameter optimization, and the same Bayesian optimization thinking applied to neural architecture search, figuring out the best architecture of things. So what is Bayesian? We'll talk about. Well, there was a guy named Bayes, a British guy, who came up with the so-called Bayes rule, right? So it is, and you have all been taught. I mean, those of you who have been with me for long enough have been through that. Those of you who did engineering math, of course, went through fairly in-depth Bayesian treatment. How many of you went through that? Yeah, Praveen, I remember you were in the Bayesian, the math of machine learning, isn't it?
Yes, that's it.
Yeah, Anil, you too, isn't it? And Nisarg.
Yes.
Yeah. So, and Pradeep, you too. You guys are there, right? And Kate.
Oh,
So, yeah. So quite a few of you. Sudhir, were you there in the math class?
No, sir.
You weren't there. Okay, so that pretty much sums it. A few of the people here are very familiar with Bayesian. So what I will do for the benefit of the rest of you, I will assume that you don't know Bayesian, and those of you who do know Bayesian, you can go have a cup of tea or coffee while I'm talking about the elementary concepts of Bayesian learning. Right? But before we do that, now I'll go back to basics and see how a typical blog, what is it that they tell you to data into the training and the test, learning and the test, right? So the test data you hide under the pillow, you forget about it completely. You don't let the model even know about it. Then what you do is within the training data set or the learning data set, you further divide it into two parts. The actual training part with which you'll train the model and the validation part or the validation set. Right? And there are all of these things like holdout sets and the cross or the k-fold and so on and so forth. But I'll gloss over those aspects for a moment and I'll just say data is now further subdivided into two parts. The one that you actually use to do, for example, if you're doing neural networks, you do your mini batches with, and to train the model in which you do the back propagation. And then the validation set in which you deliberately freeze the weights, you don't let the back propagation happen. You just do the forward part of the journey to see what is the validation loss coming through. Are we together? Yeah. You keep making prediction on the validation set, and this gives you some sense, right? Now, why is that relevant? Because then you can jiggle around with multiple learning parameters. So let's take some basic learning parameters. It could be the learning rate, right? It's a hyperparameter that you typically think when you're doing neural networks. And you can think of many such hyperparameters that you do for support vector machines is the C, the cost, the budget, right? It could be if you're using RBF kernel is gamma. If you don't know which kernel you're using, then you have to play across linear, polynomial, RBF, tan, maybe even the sinusoidal and so on and so forth kernels. You have to play with all of those to see which one works. Right? Now, you do it through the cross-validation stage. You keep on churning to see which value gives you the best cross-validation results. Right? So with that little bit of a background there, now let me start putting it to the ground. Are you guys still seeing my screen?
Yes, though it's completely black right now.
Yeah, it is black. Right. So so the basic idea that you see people mention in books, and the oldest idea is to do grade search. Let us say that you have two hyperparameters. I will call them, let me just take an example. Let's take a regularization parameter and a learning rate parameter. So learning rate alpha is one, and a regularization parameter or weight decay parameter, regularization. Let's say that you assume that you're going to do, let's say, L2, right, or something. So let's say that this is your regularization parameter, right? Now comes the problem. You have a model. Let me just take, I'll be sort of silent on what model you have, some model. This model is, if you think about it, it is the loss that you will get is, in some sense, at the end of the training, the predictions that you get, or the errors that you get at the end of it, is not just a function of the actual parameters of the model, the actual weights and biases of the model, but it is also a function of the learning rate and the regularization parameter, right, for a given input. Would you agree?
Yes.
Right. So these are your parameters, your weights and biases, but these are your hyperparameters. Right. Now, in effect, you can backpropagate the gradient with respect to loss. So, and this is the crux of the issue. See, you can do this. Right? Or let me just put it this way. The gradient with respect to the loss, you have this. And once you have this, you can do next is equal to W minus alpha grad L. So you had a gradient descent step. Now you also have backprop, which will take you layer by layer backwards. Right? And so you can do it. But now for a moment, think about the learning rate. You realize that it is not feasible for you to do this, or rather hard for you to do this. How do you take the gradient of the loss function with respect to the learning rate? It's very hard. Are we getting that, guys? Right. And not only that, especially if the learning rate is adaptive and in the process of learning or tuning the neural network during one cycle of training or a couple of epochs of training, the learning rate changes and so forth. In the beginning it's something else, later it's something else, and so on and so forth. So it's much harder to tune and know how should you vary. Learning rate is therefore a function essentially of some time, if you think as a time variable as the learning proceeds. And it's very hard to know what this is. You can't do gradient descent, you can't do backprop of all of these parameters. So which is why what people do or have always done, basic grid search says that suppose you have values like this, Learning rate is 0.0001, possible value 0.001, 0.0.01, 0.11. I'm just taking an example. You can take a range of learning rates, right? Or you can do in terms of log of it. You can say log is equal to 3, 4, 3, 2, 1, 0. You could write it like that. So you have a scale, sort of a log linear scale for the learning rate. Then you have, let's say, your regularization parameter, right, lambda. And now you can again take values from 0.00, like quite literally 0, 0.001, 0.01, and the same game, 1, 0.011. You can do this. Now, when you do something like this, what you're doing is, if you really think about it, you're doing this. You're creating a grid. Let's say that this is your alpha, and this axis is your lambda. So for different, and again, I'm taking a log minus log alpha scale. What you're doing is, and then likewise for the lambda, maybe minus log lambda, lambda scale, you're creating, there are all of these possibilities. To say I took 5 values and 5 values here. So you create a grid of values possible, right? It's a Cartesian product. So it is a Cartesian product. Let me just call it alpha A, and this is B. You're basically looking at A cross B values, every tuple that belongs to the set. Am I making sense, guys? Right? And so for each of these, what will you do? You will train the model, whatever model it is, you'll train it. You will look for loss on the cross validation set. Are we together, guys? And then, of course, you will remember that for this, you'll create your tuple. Let's say that certain value of alpha I, lambda I, and what was the loss I. You will save these values. And when you do that, you will realize that you have come up with a huge table. How many elements there would be? 5 times 5 is 25 experiments. And after 25 experiments, you would pick the best value, right? But even if you pick the best value, there is still a problem here. And the problem is quite subtle, actually. It is this. You suppose this is the best value. You can zoom in and you realize the best value is not necessarily here. It is somewhere in the region. You can zoom in and be more specific. For example, how do you know that if it is 0.01, it is 0.011, 0.009, is it 0.5 or 0.013 or 0.02, 0.03? Like, you don't know which of these values was really there. Do you see that? Because you just look at a log linear scale, and the next thing you looked at is either 1/10 or 10 times bigger than this. Are we getting it? So you have to go down to smaller and smaller resolutions. And when you do that, your number of experiments begins to increase or explode. Are we getting the point, guys? And so this has been the problem. This becomes particularly bad with neural networks. Why? Because training, let's say a simple linear regression may take a couple of seconds at most on fairly good data set sizes. Training a neural network, you guys have been doing it. Do you notice that by the time you run through 5-10 epochs of training, easily half an hour has passed or 1 hour has passed, right? So a few, and if it is a non-trivial problem, even on good hardware, quite a few hours pass by. And so you are looking at running these long experiments to find the best possible value. So grid search begins to look rather untenable, and it becomes particularly bad when you have situations like, suppose I have a hyperparameter H1, H2, H3, H4, let me just say H10. And let's say that each of the hyperparameter you try out with how many values? 10 values, right? So you realize that you are doing, what are you doing? 10 to the power 10 experiments. Because there would be these many combinations of hyperparameters. Even if you search around only 10 values for each of the hyperparameter. Does that make sense, guys? Right? Are we getting the point? It's a pretty straightforward point of combinatorial explosion, that if you have 10 values for 10 hyperparameters, you're looking at basically 10 trillion experiments. Is it billion or trillion? Billion. 10 billion experiments. Any questions, guys? So one thing is, what is the way out of this? How do we not get lost in so many experiments? Right? So before we do that, let's observe one more thing in this. Suppose that some of the hyperparameters are useless. Let's say that in this particular case, I'm just for the sake of argument saying that learning rate doesn't matter, right? So this doesn't matter. Do you realize that you did 25 experiments, but in reality, they all map to just 5 of those experiments, isn't it? 5 different values of the lambda. Do you see that, guys? If your loss function is insensitive to the learning rate, hypothetically, and it's only sensitive to the regularization parameter, then you only tried 5 regularization parameters, even though you did 25 experiments. And that was stupendously wasteful. Would you agree with that, guys? Anybody still there?
Yes.
Yeah, you would agree with that, right?
Yeah.
So it's quite inefficient. That's part of the limitation of grid search. So then somebody woke up and said, well, there's a better idea. Let's do randomized search. And if you notice, whenever we were doing hyperparameter tuning in the normal way, in the workshop, still you came to this particular session, I would always recommend that you should not use grid search, but you should do randomized search. So in particular, when you would do, Harini, if you remember, where's Harini? She's still there?
I'm there, sir.
Yes. You remember I told you don't use grid search for cross-validation.
Yes.
Use
Yes.
randomized search.
Yes.
So what is randomized search and why should we use it? To just make a picture smaller, suppose I take the same problem. So now I'll turn the table and I say that suppose the hyperparameters H1 and H2, right? And once again, this was your, let's say, alpha, and this is your lambda for the sake of argument. So suppose you have to take 25 points. Don't take a 5 by 5 grid. Instead, randomly put these somewhere. 25 points. Different, I don't know, these are not 25 points, but whatever they are, I'll just leave it as that, right? So now let's think about it. If you put 25 points, randomly, one lovely thing that will happen is, very high likelihood, there are 25 alpha values you're trying out, the H, right? And there'll be 25 lambda values you'll be trying out. Do you see that? Even though there are only 25 points, you end up effectively testing across a much larger space of values for the hyperparameter by randomizing it, right? And so let us say that the good values was around this. Now it's or around this or whatever it is, you can quickly zoom in because you have taken all of these. You can quickly zoom in and tell which local region of the hyperparameter space you should care about. And this is called the search space. In this literature, it's the search space because this is what you're searching for, the values of the hyperparameter. So far, so good, guys? Now, this has one more advantage. Let us say that one of the hyperparameters is absolutely useless, right? Let's say that lambda is useless, right? Or maybe it was the learning rate. Let me make it the other way around. I think I just said that alpha is here. What is it? Learning rate is useless, doesn't matter, and lambda matters, right? It doesn't matter what it is. So then what happens? Suppose alpha doesn't matter. Still you have, or I mean, sorry, okay, which one doesn't matter? Let's say alpha, lambda doesn't matter. You still have how many values of alpha? Quite a few values of alpha. Or the other way around, if alpha doesn't matter, then you have 25 values of lambda that you have tried, right? And so you have a better or more efficient utilization of the search space, right? So that is a randomized search. But even though it is a much more efficient use of the search space, nonetheless, it remains as a fact that you are searching a pretty large search space for the best hyperparameter. And that search space, if you have 10 hyperparameters, which is very common, you are searching in a ginormous features, hyperparameter search space, isn't it? Guys, one moment, I'll open the window, it's getting hot. So at this moment, I wish I can get some visual cues on how much we are understanding. Go ahead.
Yeah, in this randomized search, right? A worst case scenario, it will be as bad as the grid search.
In the worst case scenario, yes.
But the other point, though, I wanted to make is if we go with randomized search, it's possible that certain combinations which are important, you might just lose those, right?
No, say that again. I missed the tail part of what you said.
So, in randomized search, you're really choosing random points. Right?
Yes.
So, and then you're deciding, whether one hyperparameter is relevant or not. In that randomization, you may lose out a combination of the parameters which are more important and might make the second parameter relevant also.
Now, give me an example. Let's say that it is some value of regularization and some value of alpha, learning rate, as an example. What am I going to miss out?
No, I'm saying that you pick a combination of those two, right? So it's a combination of those.
You take a random alpha and a random lambda, and
right.
you fit that into the model and you find the loss, the best.
Yeah, I'm just making sort of a theoretical argument here that you're picking the random combinations of values of those two parameters, and then you may conclude that one of them is not relevant anymore. But while picking those randomized pairs, you may not pick the ones that would actually make a difference.
No, I don't get it. Pick the one means one of what? The right hyperparameter or the right value of the hyperparameter?
So there are only two hyperparameters, right? And then there are combinations. Let's say there are 50 combinations.
Sanjay,
and then you pick.
Use the words, don't use pronounce. Use the words. Suppose learning rate and regularization are the two parameters. Alpha and lambda are parameters.
Okay,
Now,
alpha and lambda. And in your example, you had some 50 odd combinations, right?
Mm-hmm.
And in randomized case, we may, let's say, choose, I don't know whether it's a number of combinations that we pick, but let's say we pick 20 out of those, and based on the observation, we decide that the learning rate doesn't matter. But
yes.
What I'm saying theoretically is maybe the remaining 30 combinations would have actually mattered.
No. You see, when you're doing 50 experiments, you will do all 50 experiments. You'll take all 50 random points. But what you're saying is, if I'm getting it right, what you're saying is, it may not matter around a certain value of lambda, but you may have missed the fact that there is another region or region of values of lambda where lambda matters a lot, and you didn't pick it.
Right.
Yeah, that is true. That is always a risk with randomized search, which is another reason, in fact, very good point you made, which is another reason that doing either grid search or randomized search is not a very good idea, because you're looking in a very high dimensional space. And at most, how many experiments will you do? 100? 100 is nothing, right? In a like a you need to do a million or billion experiments to even have a reasonable coverage of your feature space, I mean, sort of a hyperparameter space, search space. And nobody can do that many number of experiments. No team has the luxury of using hardware for that long, right? And sometimes people do. If a model is very, very important, they spend a long time searching for it. So the problem that happened in the industry was exactly this. These models have become huge, and the hyperparameter search space is huge. And so when you go and try to tune these models, it would burn through a tremendous amount of computational resources, right? So much of it that it was, besides being taking a long time, it was an ecological disaster to be able to, repeatedly do this and burn so much of resources for it, right? So what do we do about it? That's a question. To see what we have to do about it, let us think about it in this. See, you come up with all possible pairs or random values or combinations of, let's say, H1, H2, right? A two hyperparameter. When you run an experiment, you have either chosen the points at random, these points, or you have picked it on a grid. But when you run the experiment, let us say you can run it in parallel, like across 100 machines, but more likely you'll run it on one of your machines, your workstation, let us say, and you will do an experiment, save the result, do the next experiment, save the result, and so on and so forth, right? The thing that happens is each experiment is independent. It has not learned from other experiments that have already happened. You see that, right? Because at the very end, you'll see the results, the loss coming from all of those experiments, and then you'll decide which is the best. And then you go down, zoom in there and do more experiments. So the way to do this is, illustrate this is, suppose you have parameters, I'll just use abstract words, H1, H2. And obviously the hyperparameters in real life are many, many, but we'll deal with 2 dimensions because we have a 2-dimensional surface. Let us say that the loss, okay, or maybe even simpler, let's say that there's only one hyperparameter, right? Let me call this hyperparameter X. By the way, don't confuse it with data. Should I use X? Okay, let me use H itself because I've been saying H. Suppose this is your loss. So the best loss that you get after you've tuned the hyperparameter on the entire validation set, and this is your hyperparameter. So the L and H are beginning to look alike. So I'll make it like this. And imagine that there's only one hyperparameter. See, when you do grid search, you would, grid search, you would take equally spaced values and search for that. But suppose you took random values and did that. So let's say that the first experiment produced a value like this. The second experiment produced a value like this. The third produced a value like this, loss, right? The fourth produced a value like this, then a value like this, and a value like this, and a value like this. So now tell me one thing. If I ask you to do the next experiment, and I say you have a choice of picking the hyperparameter value, where would you pick that value from? Where would you like to do the next experiment? Which value of H? Big value, small value?
Smaller or in the middle?
And why would you pick, Rafiq, the small value? It's correct, but why would you do that?
Because there is still a gap where we haven't covered that search area.
Yes, this way. Look at the loss. Where is loss?
Usually says that, yeah, the losses seem to be lesser with smaller values.
Exactly. So you would suspect that this seems to be a more, so you would guess based on this data, right? Based on observation, you would say that loss is likely to be lower. Where? Lower in the circle region. Right? So if it is likely to be, it's more likely to be lower than in this other, let's say, rectangular region. Okay? This seems to follow after doing a few experiments, right? You can never be sure, but the observation of training with a few combinations, a few points in the search space, takes you to the conclusion that this is probably true, isn't it? So it makes common sense that you do the rest of the experiments here, the next random points you pick from here, rather than from all over the feature space randomly, right? Or do a grid search. Does that make sense, guys? I hope I'm saying something that completely agrees with your intuition.
Yes.
Right? And to do that, now let's put it in formal words. See, what have you done? You have learned from observation, isn't it? You have learned from data. In the beginning, you did not know what the hyperparameter values were. So let us say that you had it is called the prior belief. A prior belief. Your prior belief, for example, could be, prior belief could be that loss, probability of loss, or how much the loss would be, loss code. Loss is likely to be minimum anywhere. Right? So you're taking a uniform prior, means any value of h is fine. It could be, you don't know. Yeah. So you say that this is your prior belief, you're coming with no information. But gradually, as data accumulates, you now have a posterior belief. What is your posterior belief here? Posterior belief is a posterior belief. The word posterior refers to always after seeing the observations. After seeing the observations. Right? So look at this this discussion that we just did, and we are just now translating it into a more formal language. What would you say is your posterior belief? Guys? Where is the best value of the loss function likely to be?
Clustered for lower, higher
Yes,
values.
exactly. This region, right? Posterior belief would say that this region, you would say now, that if I were to draw a distribution on the values of h in the beginning, let's say prior, give a uniform, let's say that probability, let me just say probability of loss, the best value of the loss to be, then it was in the beginning, it is uniform, right? This is your prior. And then your posterior, would you agree that it is sort of seems to be more belief around smaller values, right? You believe more strongly, or you say that there's a higher probability that the best hyperparameters values are somewhere here in this region. Your posterior belief, right? Are we together? Does this make sense, guys, in this view of this picture?
Yes.
Common sense, right? And so what has happened is, what we have gone through is the classic Bayesian journey. You can, Bayesian say that there is always uncertainty. So you could be very wrong. Your prior belief is anybody's guess. You may come with absolutely no belief at all, right? Which is a uniform prior, or you might have had some inkling. For example, you could have had an inkling. Let me take another prior. You could have had an inkling that the values are somewhere here. Another prior. So what are you saying? That I believe that at this point, initially I thought it would be somewhere here, this point, right? And I am saying that the loss function, I initially believed that the loss would be minimum at that red point of the hypothesis space and around that place. So I put a bell curve distribution saying my belief is strongest at that point, that red point here, and less and around it. So you may start with the Gaussian prior. This is your Gaussian prior. But then your posterior would do this. So what is happening is your curve is, as it is seeing data point by point, as it is seeing data, your belief is adapting, right? Your belief of where, which part of the parameter space the best values of loss will be, the best scores will be, it is shifting. It is not giving up on anything. So for example, the belief that the best parameter is here at this point, way up north. I don't know, can you guys see this point? Let me call it B. Right? Do you see where I put B, guys? Yeah, this. See, it may still be there. If you look at it, my yellow posterior has not given it a probability 0 that the best loss. It may be there. It may just so be that B, so actually a B would be, let me say B, right? A B here, it should be here. The loss, it is possible that the loss here is the best. Let me say it is the best. Who knows? But it seems unlikely, right? Your observation seems to imply that it is unlikely to be there. The best losses are found with small values of H. So we deal with uncertainty. We are never too sure, right? For whatever reason, there may be this tiny island of stability around B, where the loss function achieves its absolute best score. Right? Well, am I making sense, guys? Right. So it is a question of belief. Nowhere does the value go to 0. You should make it 0 unless you have a prior reason to. But generally, you shift your beliefs. You initially, let's say that you either start with uniform, the blue belief. Everywhere, it is equally likely to be a good, the best hyperparameter value. Or you could start with the red, which says, hey, so the blue is called a non-informative prior. Can you guess why do we call it a non-informative prior?
You don't learn anything?
No, we don't know anything. It is a true acknowledgement that we are absolutely clueless at this moment, right? Picking a red curve and saying that I believe it's somewhere around this. What you're doing at that particular moment is you are saying, you know what, some experience tells me that the best value could be around this region. Are we together? And then what happens is data comes in and the data will push this. So the blue curve, for example, will start changing itself from being flat. It will become a little like this, then it will become a little like this, and then it will become a little like this, and it will become the yellow curve like this. Likewise, the red curve will start shifting. It started out like this. The next thing it will do is it will become like this, then it will become like this, and then it will become like this, and it will finally start shifting, and then it will begin to look like the red. Again, the yellow curve, the posterior curve. So it doesn't matter what prior you start with. The beautiful thing about a Bayesian learning is you start with a belief, you see a data point, you adapt, you come up with a posterior belief, right? And your posterior belief has learned from experience, learned from data, right? That is Bayesian learning. And this is a classic situation. What we are saying is, and if you think about it for a moment, you will realize that, my goodness, it makes total sense. And randomized and grid search absolutely don't make sense from this perspective. What we are saying is, suppose you did a random experiment, right? 2-3 data points you got. You may start with some hypothesis, whatever your prior hypothesis is. Let each data point, and this is where the bias rule comes in, it says that a probability of a, let me just put it this way, probability, see, of a evidence given a model. So suppose you have a hyperparameter H, right? And you have, or let's say that some value of the, wait, okay, let me change the terminology to what you'll find people use. This is your, think of it as your loss function. People often call it in this space as the objective function. Right? Think of it as your mean squared error or across entropy or whatever. This, right? Now, the probability of a loss given X, sorry, I should write it. Probability of loss, and X is the hyperparameter. Now, this looks very confusing because X we typically use for data, and Y we use L for loss and or the objective function. But I'll just stick to the language that people use. Now, this times the probability of X itself, of just the distribution of the hyperparameter, is equal to, basically is the joint probability of X and Y, which is also equal to probability of X given Y, probability of Y, the loss function of probability to the Y, right? And so you can go about saying Y over X is proportional to, this is sort of, you don't know it and you probably don't care too much about knowing about it, is proportional to probability of X given Y, probability of Y, right? So let us think through this equation, what it is saying. What is the probability of a loss function? This is your prior. What are you saying? The probability of seeing a certain amount of loss is something like blue is a certain amount of probability, is Py, right? This is your prior. What is this? Given a prior, you see an evidence. It turns out that you said loss is same everywhere. But you happen to notice that at 2 points, 1 point loss is high, another point loss is low. Now, do you still believe in that straight line, or would you like to tilt the straight line in such a way that it agrees with the data? Right? This is your data, right? Likely, it's called the likelihood. It basically says that if you believe in this, this is how the loss, likelihood of having the best loss prior is distributed. How likely is it to produce this evidence? Right? How likely is it that this value of the hyperparameter produce this amount of loss? This particular combination of hyperparameter produce this loss. And now that becomes your likelihood function. And using that, now you can come up with the probability of loss given the given certain values of the hyperparameter. This is Bayes' theorem, right? And this is called the posterior. And again, I'm rushing ahead quite a bit with the mathematics, but many of you just take it like this. If this math looks confusing, just think that prior belief learned, like posterior comes, posterior is equal to prior plus learning from data. That is the gist of Bayesian learning. Right? You see a little bit of data and you learn. So now, how do we bring that down to our case? See, what has happened is, suppose you pick some random points in the beginning, right? And what happens is that you start doing certain values of, loss starts accumulating. You may start with some prior. Let's say this prior belief that the best value is somewhere around here. And then what happens is maybe it is not here. So let's say that the best value is lurking somewhere here. Then what will happen is when you multiply this prior, and this is the mathematics of it, with this evidence, that say that you have seen only 5 pieces of evidence, it is already tilting you towards something like this. Are we together? So what is it suggesting? If this is your new y given x posterior, it has taken you towards this line. It means that you should search for hyperparameters in this region, isn't it? Much more likely to pick hyperparameters, and the next hyperparameter you should test out for your experiment from this region. Does that make sense, guys?
Yes.
Yeah, that is it. So that is the whole point. Now, why is this relevant? Because the hyperparameter space is huge. And what you're doing is you're doing just a few initial experiments, and each time you do an experiment, your prior changes, your belief changes of where the best scores are hiding, right? And so you search that part of the search space or the hyperparameter space where you believe more and more strongly, you believe that the best values of that objective function or the score or the loss is sitting there, right? So this is Bayesian reasoning. In the beginning, it feels non-intuitive because Bayesians don't come up with an answer. They say that we'll just tell you where it is more likely to be. So they go from one probability distribution to a better probability distribution. But why do we care about this? The reason we care is that a Bayesian reasoning is a very efficient means to quickly get to the solution. So, just like gradient descent and backprop is very efficient for parameter learning, weights and biases learning, Bayesian optimization has the same role to play when it comes to, trying to guess or identify which part of the search space, hyperparameter space, is likely to have the best hyperparameters or the lowest loss or the best scores in your model. So what does it mean in real terms? It means that it is a guided way to do the least number of experiments and quickly zoom into that region of the hyperparameter space where the best values are likely to be. Do you follow the reasoning, guys? Now, it is important you follow it because the literature on this is very mathematical and hard to read in some sense. So I wanted to make sure that at least you get the intuition right here. Are we getting the intuition right?
Yes.
Yeah, good. So Kate, you have taken my math class. So nice to see that you are getting the intuition. And how about people who haven't taken that? Is it making some sense? Harini,
Asif, one question here.
go ahead, Shini.
You talked about the point of point B. Point B was in the scheme of things was outlier, right? Somewhere.
I forgot.
But whereas your
Yeah.
Bayesian things are taking you towards the left side. The B is somewhere on the right side.
And that's the point with Bayesian learning and all machine learning. See, here's the thing. You go with the data.
Okay.
The limitation with all of this is, see, you can do only limited number of experiments. So if there is a very peculiar, anomalous, optimal point sitting in a little island of the feature space that you haven't explored, you won't get to it. So in other words, if you're looking at what would be a good analogy here, imagine that you're in high mountains. In US, it would be Lake Tahoe. At a pretty high altitude, there is this tiny little, obviously Tahoe is not small, but you have this lake, right, which is very low compared to the mountains around it. So you're not likely to easily discover that unless you wander into that region. Now imagine, Tahoe is of course a huge lake, but imagine a very tiny pond, a very deep, tiny pond in the middle of the mountains. You are not even going there to search for it. But that's an acceptable loss because what you want to, you have only a budget of so many experiments. Suppose I tell you, don't do more than 10 experiments. Then what is the best way to do the experiments?
Got it. So given the resource limitation,
yes,
lead you to the best possible alternatives.
Yeah, and if you know Bayesian reasoning, then this is an absolute no-brainer because you would realize that Bayesian way is the shortest path in any space, in hypothesis space, to find the best hypothesis, right? And we went through that process in the math class.
Asif, I have a quick question.
Go ahead.
So you changed the distribution. How
how does that happen? Actually, I thought
How does
everything.
that happen? All right, let's take an example, right?
Asif,
Let me make
I'll throw in one more question so that you're addressing both together. Now, there's an implicit assumption here that the underlying distribution follows a continuous function.
that is a given, isn't it? So think about it, the learning rate, right? If you change the learning rate by minuscule amounts, do you really expect your objective function or the best loss for those two different values, cross-validation losses, to be radically different? You don't expect them to be.
So that part I would agree, Asif, but we are kind of saying these are all hyperparameters.
Yes.
And when we look at learning rate as an example of a hyperparameter, the intuitive sense is it is continuous.
Yes.
Can we say that for all the hyperparameters?
No, we cannot. We cannot say that. And that brings up a very interesting issue. So some things are not continuous. For example, which algorithm to pick is not a hyperparameter.
Yeah.
And so, like, I'm motivating it with continuous because continuous, the intuition becomes clear. Now, there are techniques that you apply. And so then it gets into some very interesting territory like bandits and so forth, learning, which I haven't taught you. But so, okay, see, into this game, right, some very interesting things come. And before you know it, even reinforcement learning has walked in. So we won't get there. To have the intuition simple, just think of continuous parameters for a while.
Okay.
Any other questions, guys?
Asif, the other question is, let's say there's one parameter and we are doing a log search, binary search.
Yeah.
Underlying assumption on a binary search is like the distribution remains the same, but you then move your search criteria by dividing the data. You do a tree decision and then move your search. And in the Bayesian, can you give us an intuition? I mean, the whole search space is much faster than the log search, right? If it's just
yes. See, here is the thing. Given, so let me summarize it this way. What grid search and randomized search suffer from when they're searching for the best hyperparameters is that you do an experiment and it doesn't contribute to the next experiment, where you should do the next experiment, isn't it?
yes.
That is the main problem. Now, Bayesian, almost by construction, is saying what is the maximum learning or information you can derive from the experiments that you have done and the results you see from them, right? Because that is the evidence. And you basically say that, see, I have this belief, and I'll give you an illustration. Okay, let me, why don't I illustrate it with an example? Because some of you said, what is Bayesian learning? So Balaji, hold that thought in your mind and see if I answer. Let us say that you fall asleep in a plane and the plane doesn't land where you think it should land, right? Or in US, there's something very interesting. If you go into a witness protection, apparently, I'm told, I don't know how true it is, you don't know till you are in the flight where you're going to land, right? Because to protect your identity, because to save you, the information is given to the least number of people. And even you are not given information because then you'll start preparing. If they tell you you're going to the desert, you'll start buying all sorts of equipment and people can guess. Or if they say they're sending you to Seattle, you'll start buying an umbrella, right? So I've heard, I don't know how true it is, but so they tell you on the plane. Now, let's say that they give a location, right? And it is, let's say the location name is some very generic name, Georgetown, right? Now, Georgetown can be anywhere, right? I think this, the whole Western Hemisphere is dotted with Georgetown. In India, it would be Rampura. I'm sure there's a Rampura all over the northern belt. Right? So now the question is, you're trying to guess what the weather there is. Let's take two extremes. You say, is it a desert or is it basically rainy all the time? Right? So you have a choice now. Let's say you landed there and you make a guess. What guess you made is two, and I'll make it discrete so that it's easy. So you say that a probability of rain, or no, actually continuous, probability of rain, if it is a desert would be 0, right? Let me just say the rainiest place it will tend to 1, right? And by the way, then you realize that between this, there's a whole range of values possible, infinitely many values possible, right? So, for example, if you end up in, I don't know, Seattle, it would be somewhere like this. The probability of rain on a given day is, would this be right? 80%? I don't know, right? And suppose you land in California, the probability of rain would be something like 10%. And let's say somewhere in here, there is Arizona, it would be, let's say that this is 15%, 0.01, maybe, actually not Arizona, Colorado, let's say, or something like that. Okay, Arizona would be this, and complete desert would be, what is it, the Death Valley would be 0, something close to 0. But you don't know what is happening, right? So I'm just taking an example that it could be any one of these places and infinitely many in between. So you start with a prior belief. Actually, let me do one thing. This py, the prior belief, right? I tend to write it not with a p, but to make my meaning clear, I use this pi, because pi reminds me of prior. Can I use pi? Just don't take it to be 3.1416. All right. This is just belief before I know anything. Prior belief. Are we together, guys? Prior belief. Now what happens is you go to sleep and wake up in the morning, and let us say that it's raining. What now? Ask this question. We will take these cases like 1, 2, 3, 4, 5, and we are trying to decide between these 5 cases, right? So let me go again here, a desert. Now, what is the likelihood of rain happening if your prior belief is correct? So if your belief, if your prior belief that it's a desert is actually true, what is the probability of having seen rain? What would be an answer for that?
0.
0. It would be actually 0, right? And what would be the probability of rain here? 1% chance of rain, and the first thing you notice is that there is a rain. Well, it would just sort of it rained. So what is likely? How likely is it that this would happen? So, you can go here, and this, if it says that this would be 1, right? Very high likelihood that it is raining, right? And you can work out all the other in between stages. And then what happens is that if you multiply your prior with your posterior, you would realize that the problem that at this moment, where you have landed up, this is multiplied by this is 1. You will realize that it rains, right? Now, let us say that the first day it rained. Second day, no rain. So what is the likelihood of that for number 5? In the rainiest place, you didn't see a rain. What's the likelihood of that? If the prior probability is 1, what is the likelihood of seeing that evidence?
0.
0, right? So you realize that what happens is that when you multiply your prior with your likelihood functions, reality begins to come out. And here I've taken extreme cases where some things go to 0, but what will happen is this completely got eliminated. This got eliminated, this got eliminated, right? Let me just say that this was 0.001. Certain things, they just begin to get eliminated, and the probability of certain other things will start increasing. Isn't? At this moment, you had a uniform probability. The prior was, each of these is equally likely, right? Desert is equally likely. It had a 1/5 the probability, right? Arizona, all of them had 1/5 probability. Because you don't know, you could be in any one of those 5 cities or 5 places. But the more you see the evidence, for example, one day it rained and one day it didn't. Already the desert and the rainiest places are out. but their probability needs to shift somewhere, right? So what will happen? The probability of these things, half and half. So these things would go up, right? And now let's say that for 3 days in a row, it rained. Now what happens? You would realize that 3 days in a row it rained. The probability, sum of this thing that it doesn't rain much will go down. This will go down, and this will start climbing up, right? And so what are you noticing? You are going from a flat distribution to gradually you are going towards. Do you see this, guys? If I were to make a continuous thing here.
Yes.
You're getting it. So that is the magic, guys. That's the most amazing thing about Bayesian learning. In fact, it's the foundation.
Prior is set distribution, right? Like the pi.
Yeah, 1/5, 1/5. See, in the prior, suppose you didn't know anything about where you have, where you have landed. You could have landed in 5 places: desert, Arizona. Arizona. Desert. Think of Death Valley, Arizona, California, Seattle, and the rainiest place in the world. So in the beginning, if you don't know anything, I take you out of the airport and put you into a hotel, and you can't see out. You could be in any one of the 5 places, isn't it? Would you agree? So how would you distribute your probabilities? 1/5, 1/5, 1/5, 1/5, right?
Yes.
So I'll give you one intuition, guys, that I use when thinking Bayesian. I think of probabilities as sand, and I think of 1 unit of sand, 1 bucket of sand, right? And each of these situations, you need to pour sand there based on how much you believe that is true. So out of these 5 possible scenarios, you have 1 bucket of sand. Is there any reason in the beginning, without seeing data, for you to put more sand in one place than the other? Probably not, right? So that is a non-informative prior. You put equal amounts of sand in each of the 5 possibilities. You're betting equally there on all 5. Does that make sense, guys?
Yeah.
But next morning, what happens is, oh, good grief, it rained. The moment it rained, your desert is out of the window, right? It doesn't look like Death Valley anymore, isn't it? So you will take that sand and put it somewhere. You will shift it to the other 4, isn't it? Then what happens? Then the second day, it turns out, the first day it rained, and the second day it turns out it did not rain. That screws up the other end of the spectrum also. It is not the rainiest place in the world. You see that, right? And so you take the sand out of there also, and you take it out. And so what happens? Sand gradually keeps moving out of what is not true or not likely to be true to where it is. Data is doing what? Forcing you to move the sand out of the unlikely things and move it to more likely things, things that are more likely to produce that evidence that, oh goodness, one day it rained, one day it didn't rain, and then 2 days afterwards it again rained, right? And so what it will do, you have 3 days of rain, 1 day of no rain, and gradually things are now edging more towards a rather rainy place, but not necessarily the rainiest place. And more data keeps coming, and what will happen is your sand hill will become more precise. It will become sharper, higher. Am I making sense, guys?
Yes.
Right? Another way to think is, suppose you have a very strong belief. You saw the aeroplane heading west. And so in the beginning, you said, you know what, I'm not going to distribute it equally. On California, I'm going to place a bigger bet, right? And then in Seattle, and rainy, and this place, like this, different amounts of sand you did. Or maybe you happened to look outside the airplane window and you saw you were heading towards the west, right? Something like this. Now what happens? California, it rains only 15% of the time, but your evidence seems to show you that it's 75% of the time it's raining so far. So what happens? You begin to now move towards Seattle. Your belief begins to drift towards Seattle, right? So this sandhill begins to get smaller, right? And this one begins to rise up. And this, of course, all this sand moves this way and all this sand moves this way. Do you see how it goes? So what it means is that with enough data, with sufficiently large amount of data, you will hit upon the right answer. Doesn't matter where you start from, which prior belief you start from.
Asif, the confusion was the wordings posterior, likelihood, and the prior. I don't. Can you rephrase it in this context, which is
Yes, yes.
prior?
So a prior belief is that which you believe before before morning happened and you saw whether it rained or not. It's
Okay.
your belief of where you are. Are you in Death Valley? Are you in Arizona, California, Seattle, or the rainiest place? One of the 5 places. So what is your belief? How strongly you believe? So you have a unit belief, right? You need to divide 1 bucket of sand across these 5 scenarios. How would you break it up? And it's completely up to you. You may equally divide it, or you may believe, you may have a hunch that, you know what, it is California. Frankly, most people who go into Witsec, they would love to come to California, isn't it? So, well, okay, there you go. So it doesn't matter. You distribute your belief whichever way you like. You put your spread out your sand whichever way you like. That is your prior. Then next day it rained. Likelihood is the probability of this hypothesis producing this data, this event. So if your hypothesis is a pure desert, what is the probability that it would have produced rain? Balaji, what would be the probability that you are seeing rain if you're in a desert? Zero.
Zero.
Now what just happened? So likelihood is the probability of the evidence being there given this,
given the prior.
given that, yeah, that value of the prior, right? So that immediately you say the likelihood is 0. So the posterior is proportional to likelihood times prior. So that one thing goes out of the window, because initially you started with, let's say, equal prior, 1/5. 1/5 times 0 is 0. So your posterior belief that you're in the desert has immediately died.
So the posterior slowly becomes sharp and sharp.
Yes, exactly, exactly. And in fact, you know, Bayesian learning is the heart of science. The way we say it is that it doesn't really matter what your prior is, what your initial belief is. For example, you may say, you know what, the sun is going around the earth, right? And let's be even more particular. All the planets are going around earth, not just the sun, right? But then you see some evidence. So long as you're willing to adjust between possibilities, there is an alternate hypothesis that the earth goes around the sun is there in your mind. Gradually data will do what? It will start shifting. The evidence will start shifting and favoring the hypothesis that says that the earth goes around the sun, isn't it? Do you see that, right? Right? And so soon you will come to the conclusion that all the planets are going around the sun. So long as you are willing to admit that as a possible hypothesis, right? It is there within your horizon of possibilities.
Asif sir?
Yes.
I found this Bayesian to, get the understanding intuition easier when combined it with the concept of entropy. So I think it is little difficult to for everyone. It will be little different how they get the intuition, but initial understanding it takes time to build.
That's right. No, you said that you found it easier to get it
with the concept of entropy. They
How would you argue with that? Would you like to explain to people? That will be fun.
I mean, the basic understanding is that when we know this some information, then entropy basically reduces. The posterior entropy breaks down when we have some evidence.
Posterior will always have more order, less. Yeah, less entropy.
Asif?
Okay. That's one way of looking at it. It has more. It is more information rich than the prior. Yeah,
Correct. And sir, you have explained it, I think, a few weeks back. Get Bayesian the Getsen theorem.
That's right. Yeah, I remember. Somebody else was asking a question.
Yeah, Asif, so this prior belief, and we move towards the posterior, or the posterior gets better and better. The data that we use, is it the subset of the data gets used when in the iterations that we move, or is it the entire data set?
Sanjay, you're missing the point. Remember, you have taken the data, you have a training. Remember that you have data into 3 parts. Let's go back to data. I guess this gets confusing. By the way, we are still not done with the whole theory has some very interesting things, surrogates and whatnot. We'll come to that, but let's get there. So you have data, training data, validation data, and this is the test data. Test data you take and hide under the pillow.
Yeah.
You don't get to see it. Now what happens is you build a model M with a hyperparameter value H, right? Now what will happen? For each value of H, the model will produce a certain value of the loss.
Yeah.
Right, the best loss. On the validation data set, it will produce. So you keep the validation data the same, but now you're generating new data for H1, L1, H2, L2. Do you notice that? You're creating new hyperparameter search data. You're doing this experiment again and again, these trials, and for each value of the hyperparameter, you're finding a certain value of the loss, validation loss. Sanjay, are you getting that?
Yeah, I guess my question was on the input data.
No, input data, you don't care. Whatever training data you started out with, you freeze it. You use that again and again.
When you're going through these iterations, right? You're using the entire input data again and again.
No, okay. Look at this picture. You're not. You're removing the test data out.
I got the test data.
If you just mean this, yes.
Yeah.
You're using that again and again. The same. You're not varying the data in this process, right? And so the question is, guys, see what happens is that the loss, the amount of the objective function, think of it this way. This loss or this the target variable, this is your y. Y is in reality some unknown function of x, where x is the hyperparameter. Hyperparameter, right? Or let me be more particular, it is actually the x vector, because there are multiple hyperparameters, then you're searching for a point in the hyperparameter space. But let me keep it simple to one dimension. You know that somewhere in there, and this point has a problem, you cannot, it's not that easy, because what if this function is like this? And you need to find this point, isn't it? This is your y. The minimum of the loss is somewhere here. And in the hyperparameter space, x is equal to the hyperparameter space. Right? So how do you systematically find that? That is the problem we are solving. Right? That is the problem of model tuning. Now, oh goodness, we're getting close to 10. So how we do that is actually very interesting. I unfortunately lost an hour, otherwise we would have finished it. We need some time to finish it. Maybe in the lab time, I'll add some. Do you guys have another few minutes? Can I take another half an hour?
Yeah.
Okay. So the way you do that is, see, this is unknown. Right? And it's a function, it may take whatever value it does take. You, first of all, you make it into a minimization problem. Huh? So suppose you want to find the most accurate model, you wouldn't take, you want more high accuracy, then you take the negative of accuracy. So you try to minimize the negative of accuracy. So you always take a minimization problem. So what you're saying is that what is the argmin value of x for the function fx, right? Y is equal to fx. What is the best hyperparameter? So x star, the best hyperparameter for which this objective function, oh goodness, what am I doing? This x star is equal to this. This is the problem that we are solving. But how do we solve that? That is where some will, now I've given you the physical intuition that we will be using Bayesian optimization to do it. Now, how do we do it? So there are many ways that people have developed. I will tell you the very popular and very good way. And it uses something called a tree structured Parson estimator, pretty good word, big word, trees Parson. It is typically written as TPE, tree structured Parson estimate. Sometimes people use this. You could use whatever you want, and Gaussian processes are also very common. Now, I won't talk about Gaussian processes because I haven't taught you Gaussian processes yet. It's a very Bayesian thing to do. Right? Even in the engineering math, I didn't cover Gaussian processes. It's a little bit interesting, but you never seem to have enough time to get around to it. So we'll cover the TPE, the tree structured Parson estimator, or just tree Parson estimator. But before I go there, so let me give you the steps. First thing to realize is you don't know why is it fx unknown. And you cannot analytically find it. Why? Remember, you can't do gradients. Some of the parameters you can't do the gradient of, especially if they're categorically lost, you can't do gradients and so forth. So we need to do this. So what you do instead is you create a surrogate function, surrogate, right? And a function, which answers a different question. You come up with a distribution of y given x. Which value of the hyperparameter makes at that moment, what do you think y will be? You know, high value of y. I mean, sort of optimal value of y would be. At which place, given this x, what is the likelihood or the probability? So let me put it more precisely. Probability that at hyperparameter x, you will see a score value y, specific value y. For y will take on that particular value, right? Y could be the loss, for example, mean squared error, then you would see 100 as a mean squared error. So this is a probability distribution. Now the question is, given this probability distribution, what you do is you come up with something. So actually, we are running out of time. It's better not to rush through it. Guys, is it okay if I stop here? Because the surrogate functions and the things that we're going to talk about, the tree Parson estimator, they are a big topic. We need to give it an hour or so to do it properly. I think it's better we do it next time, and I use this time to review what we have talked about so far. Would that be okay, guys?
I think that's better, Asid, because some of us will.
Yeah. So let's do that. Let's see what we learned so far. And I apologize for the abbreviated time. So I said that the traditional, let us see in the order of goodness. Most people don't do cross-validation search. They apply a machine learning algorithm, scikit-learn or something, just out of the box, right? And even for which algorithm to use randomly, they'll pick one. That is as bad as it can be, right? Because evidence shows that sometimes proper hyperparameter tuning or choosing the right algorithm can give you orders of magnitude better performance, huge performance gain. So you should do that. Now, when you have to tune the hyperparameters, you identify the hyperparameter. The old method used to be, and by the way, you'll still see it in interview questions and books and so on and so forth. Grid search. Grid search has been sort of the staple diet in the industry for many years to do hyperparameter tuning. Grid search has a limitation, which I mentioned to you, many limitations. First of all, it doesn't efficiently search the space, hyperparameter space. Secondly, if there is a useless hyperparameter to which the objective function is not sensitive to, loss is not sensitive to, then basically you do 25 experiments, but only 5 are valuable. So not very useful. The other problem with this is, of course, the combinatorial explosion. Now the combinatorial explosion is terrible. Even if you just pick 10 values for 10 parameters to do that, you're looking at 10 billion experiments, which is not really feasible, right? So what do you do then? And people have been doing that. So what people do is they are more parsimonious. They keep hoping that they will tune only 2, 3 parameters, and they take 5 values of that. Even then, they're doing 125 experiments. That's a 5 times 5 times 5. Right? So it gets slow. The second, a little bit better, is you suppose your budget is to do 25 experiments. Instead of picking them on a grid, pick them randomly. It's a more efficient utilization of the search space, especially if some hyperparameters don't matter at all. Right? You're more likely to get to the close in the neighborhood of the right where the objective function achieves its optimal value. You'll get closer to that more likely because you have more points along this every hypothesis or every hyperparameter axis. Then we learned about the prior belief. A prior belief could be loss is likely. You see, prior belief is where do you think is the optimal value, right? Put a probability value, all of it coming to 1. Probability distribution means you have one bucket of sand. You can spread it everywhere, but it must all add up to one bucket of sand that you're spreading over the features, over the hypothesis space, right? Putting it in a very intuitive manner. That's it. Exactly one bucket of sand, no more, no less. You need to spread it over so that the amount of is some probability density, and all those densities then add up to 1. Right? So that's your probability distribution. Now you can start with prior belief. You may say, I don't know, I'll spread the sand equally over the whole hypothesis space, over the whole hyperparameter space. If it is like, we took this example, a discrete example of rain. You say, well, I don't know which of the 5 places I've landed in. Or you could have a hunch. It is perfectly okay to bring in hunch. It's just being subjective is actually good in this space, a Bayesian learning. It means that you brought some prior which is informative. Something tells you that, or your past experience tells you that you need to pour more sand on one of the scenarios than on the other, right? Or you need to pour more sand on certain regions of the hyperparameter space, which you believe is more likely to be fruitful or have the best answer, then you put in another. And then you do the experiments. You do this, you train the model again and again and again. And at each time you still make your table of X and Y, given a hypothesis, how much is the loss? You do that. But the beautiful thing is that after every experiment, you learn from it, right? And you keep on learning. So you learn from every data point that happens. And you come up with a better posterior, means you move the sand around, right? To agree with to make the evidence more likely. And then what happens is, suppose you have 5 points you have tested out and your likelihood is whatever it is, loss function is whatever it is, you look at the likelihood. What probability distribution could have produced that likelihood? It becomes sharper and sharper. Right? And your probability distribution function will start, or the surrogate function, it will start accumulating at the right place, near the optimal value of the hyperparameter. So to do so is the Bayesian optimization, using Bayesian hyperparameter optimization. So next time, guys, what we'll do is we'll do a lab where you'll see these things in a very real way. But when you see this, unfortunately, those libraries have become good. They become a few liners, and you don't see what is happening under the covers. You just see the power of them working and doing it. Now, but then we will take out some time aside to finish the theory of this, especially at least one of them. We won't do Gaussian processes, but I would like to do at least the tree parson estimator algorithm and explain it in detail. It's worth learning it once at least. But leaving the theory aside, the big message these days is, guys, all models come with hyperparameters, right? And go shut your books that tell you to do random search. Grid search, they're hopeless. Even the randomized search, no, right? Always use Bayesian optimization because it is the most efficient means to finding the best hyperparameters. Right? Now, you may say that, when you do this update of your posterior, you're doing computations. That computational cost doesn't matter. In grid search, you don't do anything. You just randomly go from, I mean, you just go from one point in the grid to another. In randomized search, you go to random points. There's no computation, but in this, there is a computation. The computation of finding the posterior, right? And belief, posterior probability distribution or surrogate, and then choosing the next point to look into. But what happens is that search of a posterior and then choosing a hyperparameter point uh, based on that probability distribution or sampling from that probability distribution takes a couple of seconds, whereas typical machine learning algorithms, especially the hard ones, um, they can go on for otherwise hours and days, right? So that cost is nothing compared to the inefficiency of not using Bayesian optimization. So that's the big message here, guys. So this is the concept of Bayesian optimization and Bayesian hyperparameter tuning. I would say once you do the lab, make it a core part of your arsenal. Always do that. Now, you may wonder that, see, I don't know if you guys ever wondered, you realize that I did not ever formally teach you grid search and randomized search. I sort of told you that, yes, you can do that to find the hyperparameters. Right? But I never went fully into it and says, as a best practice, you must always do it. Right? And now I'm saying the reason partly is I was waiting for the day I would introduce you to Bayesian optimization. And more than that, now I would like to exhort that once you learn the Bayesian optimization, always keep it as a part of your definition of done or getting your modeling done, to always use Bayesian optimization to find the best values of the hyperparameter. Just tuning the hyperparameter can take your accuracy from 10% to 80% sometimes. It's like tremendous, right?
Asif sir,
Yeah.
is there any limitation um, on using Bayesian learning basically? In
See,
terms
Bayesian learning's limitation is, see, compared to not using any hyperparameter tuning at all, right? Bayesian is expensive, but compared to grid search, random search is cheapest. It's the cheapest way to find the solution.
right.
The theory people find hard, right? Unless you have a Bayesian background, like you are getting it because you have come to the math class.
Right.
When I go into the TPE and so forth, and these algorithms, it gets a little bit even more involved in Gaussian processes and so forth. So it's more the scale factor. More than that, I don't know. Like I can't think of any limitation. Actually, the tragedy is it's so poorly understood. Most books, at least the ones that I saw, the typical books, they don't have a chapter on a Bayesian optimization. Those of you who have taken different courses on neural networks before me, before coming here, did you encounter Bayesian optimization, Bayesian hyperparameter tuning? Anyone? That instead of randomized search, grid search, you should use a Bayesian hyperparameter tuning. Did anyone of you go through that?
No, Asif.
Don't. Most books, most people don't even know. It's like, people are digging ditches when a big mighty river is flowing next to you.
Does the size of data or number of the size of data make any difference, sir?
The
On
bigger
use?
the data, the harder the training, the more you should use Bayesian. Right? Because now each cycle through the data takes a long time, right? One epoch is going to take a long time, isn't it?
Right.
All the more reason that you limit the number of experiments you have to do or trials you have to do to find the best hyperparameter.
Right.
See, there's no reason. I mean, it's very hard pressed to find a reason why you wouldn't use this, except for simplicity. Sometimes you're pretty sure hyperparameters don't matter. Pick any you like, right? If you're pretty sure of that, then of course don't bother. But if you're going to do hyperparameter search, for heaven's sake, use Bayesian hyperparameter optimization.
So far we have not used in any of the problems we solved lab
Right.
right?
But now that I've introduced it, now hereafter you should.
Okay.
Right. So it's like ensemble. Remember, before I introduced ensembles, it is like one algorithm. But once we did ensembles, I said that you should always create ensembles, isn't it? It always outperforms. So it's like that. I'm introducing you to another concept which you should always use. Yeah. And also, I mean, frankly, it will make you stand out because most people are, their learning is not that deep. They are not well versed with all of these things. The more you use it, the better your results compared to others, and the more you stand out.
I was I was reading one article today, and there it was for weather forecast. They always use ensemble method.
Oh, of course, thousands of models go into it.
Right.
Thousands of completely different models go into it.
In one of the mathematics, basically the BBC mathematics lecture, they was talking about this
Oh,
one.
that one, that series. You have to watch that series.
That is really good.
Nice, I'll watch it. I think you're beginning to love mathematics now, Pradeep.
A little bit.
Nice. All right, guys, I'll end this. I'll definitely end recording. We can continue talking. And I apologize again for this situation. Unfortunately, guys, I can't help it. I don't still know, but it is possible that next week we may have a similar situation. Right? So if it permits, we can either move it to Tuesday if that happens, or just start a bit late. Which would you prefer, guys, for next week?
Tuesday will be better.
Yeah, assuming that my Tuesday doesn't get occupied these days. It's the end of the year, and we are going through a lot of.
So Asif, are we meeting tomorrow?
Yes, of course, we're meeting.
For the paper reading?
Yeah, we are of course.
You said it. What time? 7:30.
We are going to meet at 7:30. We agreed on 7:30, isn't it?
7:30. Okay.
Yeah, let's meet at 7:30. And guys, I'll post this COVID paper. If you get a chance, please do read it. It's a good paper. It will give you a sense of how these things actually solve very real problems that we all are facing. And when you look at the neural network, there's nothing mysterious about that neural net. The only thing mysterious is how in the world did somebody think of it? Okay? You know all the pieces of that neural net when you look at it, the COVID net.